our first question, which was submitted by Letao Jr. Letao, thank you so much for this. There's a few questions on your page, and I've seen you've highlighted 3 of them. I want to do 4, and the reason for that is because the 4th one could be tricky and could be answered in 2 different ways. Let's start with the first one. We have the square root of 2 minus x, which is equal to x minus 2. Now, folks, on the outset, you can see the only difference we have here is the fact that the one side has got positive 2 minus x and the other side has got x minus 2. Okay, so that should help us tremendously in solving this problem. Let us see, first of all, what are the restrictions that we are going to function under here related to x. So our restrictions, first of all, folks, is as follows. Our restrictions on the variable, which in this case is x, is underneath the root. At school, we're working with real numbers, which means what's underneath square roots, in this case 2 minus x, has to be bigger or equal to 0. If they're negative, then you're working with a complex number, and complex numbers are awaiting you when you go to university. You're going to learn about complex numbers, imaginary numbers. Okay, so that's the first restriction. The second restriction is in front of this square root, there's an invisible positive. Because on the right-hand side, there's a variable x, we have to make provision for the fact that this x minus 2 can be 0, but it definitely has to be positive or 0. So if we look at our 2 restrictions and we clean this up a bit, we get x is bigger and equal to 2 is our one restriction. And then it has to satisfy what's inside the root, which will then be minus x bigger and equal to minus 2. We transpose the 2, and that means if we divide by a negative, x has to be smaller or equal to 2. Now, folks, if you look on a number line, there's 2. Bigger and equal to lies to the right of the number line. Less than equal to lies to the left. So it seems like, and this is the key thing, it seems like x equal to 2 is going to be the only possible answer that we can get from this equation that we're looking at on the screen. Okay, so if you don't believe me, I would end it off here. I would say x is equal to 2, but just be careful because there are other roots involved here. Grade 11s and matrics, this is particularly for you. If I now start my method of squaring both sides to try and solve this equation, then I'm going to end up with, let me change color, we're going to end up with 2 minus x on the left-hand side is equal to the square of this, x minus 2 all squared. Now, folks, we know from earlier mathematics in grade 9 that if we have a minus b and we square it, it is the same as b minus a squared. Without the square, this is obviously not true. So a minus b is not equal to b minus a. With the square over those 2, it is definitely the same. So I'm lazy here. I want to change the second bracket. So I'm going to say that this here is nothing other than 2 minus x all squared. Then I'm going to throw everything to one side. I'm going to end up with 2 minus x all squared minus this is in a bracket. I'm going to throw it to the other side, so it becomes minus 2 minus x, which is 0. You can see there's a common bracket, so if I remove it, 2 minus x is out. I have a 2 minus x minus this 1 that is left. Remember, if I remove the whole term, there is 1 times whatever that was. So I need to leave something in its place there, so that if I multiply that bracket back, it goes back into the position where it was before I removed it. Okay, so let's see what happens here. This is now a product, folks, and you've learned at school that if A multiplied by B is 0, then it means A is 0 or B is 0. So that's what I'm going to be using here. So 2 minus x is 0, or minus x, that's a plus 2 minus 1, so plus 1 is 0. And there I get my one result is x equals 2, as we suspected, or x is equal to, where are we here? That jumps over, so x is equal to 1. Now, folks, x equal to 1 does not satisfy this restriction. It satisfies this one, but it's definitely, it satisfies the minus 2 as well. Okay, but it does not satisfy this one. It satisfies this, does not satisfy that. So we cannot sit with x equal to 1 as an answer. The only solution that is valid in this case is the x equal to 2. Now that was the interesting one I was talking about, because those numbers are the same. Okay, so it's a beautiful question. It has one and only the one answer, and if we check it with our restriction, that is where we are going to get our answer. Okay, let's move to the next question I've got ready for us. It's still busy with Letau's questions. Letau, this was a beautiful question. This question is asking us to solve for m and q. Now, what makes this very, very interesting, folks, is the fact that they said y is equal to something else. And you've got to know how to use those two things. The statements that they've given you here, there's a double equal sign in this, let's call it an expression or an equation. It's actually an equation. So both of these two things are equal to the same y value. Okay, so you are not going to isolate an x, for instance, and substitute the x like you usually do when you do a simultaneous equation. This one, we're going to introduce a special way to do this. They told you these two things are indeed equal. Okay, and to deal with it as equal, you have to just ignore the y in the front. That was just there to say what you might be doing next will be the right thing to do. So we're going to ignore the y, and we're going to say, okay, let's work with twice x minus 2 squared plus q being equal to twice x minus 5 x plus m. Now, I can hear some of you, when you saw this, were thinking, this must be a simultaneous equation. Now, remember, your methods for simultaneous equations, folks, is you find the one variable, get it by itself, and then substitute in, and then you use your algebraic methods to try and solve the variables that they're asking you to solve. But in this case, you needed two equations because you have two variables. Okay, and we had our two equations given. We were given y is equal to this, and y was equal to that. And instead of substituting and isolating and doing all of those things, we use the fact that they equal. So let's see where this takes us. This gets us to twice x squared minus 4x plus 4 plus q, which should be equal to twice, if I distribute over here, x squared minus 5x plus, mx minus 5m. Okay, here I can still distribute the 2, there I can distribute the 2, so let's go for it. 2x squared minus 8x plus 8 plus q is equal to 2x squared minus 10x plus 2mx minus 5 becomes minus 10m. Okay, so now we can try and solve the variables. And how am I going to solve them? Folks, listen carefully. It's called equating the coefficients. So we look at what the coefficients are in front of x on the one side of the equation, and because these two things are equal, I have to have the same thing in front of the x squared on the other side. Okay, let's see if that's the case. Here I have 2x squared. Oh, lovely, and I've got 2x squared there. So that doesn't really help me to find q and m. So let's focus in on the variables, or the x's, where the q's and the m's are. And I think the first one will be to work with the x's. I have a minus 8x on this side, and on this side I have two of them that's related to the x. So I'm going to say, by equating my coefficients, I'm just going to stop that long word over there, I have that minus 8 has to be minus 10 plus 2m, because that is what is in front of the x on both sides. And look at that, folks. You now have generated a new equation that can help you solve for m, just by equating the coefficients. Don't forget this method. It's the first time in a long time that I see a question like this on a matric paper. So thank you very much for that, Letao. That gives us a lot to think about. Okay, let's try and solve this. The 10 goes to the left. I have 2m, which is equal to minus 8 plus 10, which is 2 in this case. So m is indeed 1. Now I have the value of m. So if I want to now find the rest of this, there is what's left. My constant on the left-hand side is 8 plus q, nothing I can plug in there. The constant on the right-hand side is minus 10 m, and m is 1. So we can leave it as minus 10. So what's left for us to do is to throw the 8 over, and I end up with q is equal to minus 18. Lovely question, absolutely beautiful. Two equations were given, both equal to y. You had two variables to solve. The one variable was only in the one equation, the second variable was only in the second equation. So you had to use the fact here that the two things are equal to each other to be able to solve for m and for q. So you ignored the y. You multiplied out, you distributed, and then this is the key thing to answering or to solving your two variables. We call this, we are equating coefficients. The coefficients are the things that are in front of the variable, which in this case is x. Okay, m was 1, q was negative 18. Let's look at the next one. Now, this one is a monster. When I saw this, I thought, oh no, what is going on with this question? There's so many x's here that one is tempted to say that if x is 1, it works for everything, so x is equal to 1. Now let's see if there aren't anything that we need to really think about when we approach this question. Let's start with our x's. Let's try and see what happens here. We have an x, then we have in its power a x to the power 1, and there I have a x to the power of a half. Remember the root of x? The nth root of x to the m is x to the m over n. In the square root, there's a 1, the invisible 2 here, and there's a 1 inside, so the power becomes a half. On the right-hand side, we have x multiplied by the x to the power of a half. All of that is raised to the power of x. Okay, so I'm going to apply exponential laws here. The bases are the same. It rings in my ears that I need to use exponential laws. So let's have a look. Here the bases are the same. So we know that a to the m multiplied by a to the n, if the bases are the same and I multiply them, remind yourselves, I have to add the power. That is what I'm going to do over there and over there. In this whole problem here, we have got something that's raised to a power. Now, that will be a to the m raised to the power of n is a to the m multiplied by n. That's the only time where you multiply those powers together. Okay, so let's have a look at what we can do. I hope we can get out of this mess. Let's see. Over here, I end up with x to the power x. Now 1.5 we're going to write as a power of 3 over 2 is equal to x to the power of 3 over 2 to the power of x means I must multiply that power with x. Now folks, here I'm ready to make my job much, much lighter than what it is. My x's are both in the base. The two bases are indeed the same. Okay? It's x that I'm solving. So I don't want to cancel that x. I want to get to the x's in the power and bring them down. So I'm going to take the log base 10 on both sides and see where this takes us. Let's do that. If I get now the log of x to the power x to the power 3 over 2 will be equal to the log of x to the power 3 over 2 times x. Now I know I brought the x in. The x has to be a positive number because the log of a negative number doesn't exist. Now folks, that correlates beautifully with what we've learned in our lives regarding exponents. The bases in an exponential question, the base has to be a positive number and the base cannot be 1, else it's no longer an exponential graph. It's a linear or a horizontal graph. Okay, so we can also not let x be equal to 1. So there's two restrictions on our solutions here. The powers come down. I get x to the power of 3 over 2 multiplied by the log of x is equal to 3 over 2 times x multiplied by the log of x. So what log law am I applying? I know that the log, let me do that in white up here. The log of anything raised to the power comes down and I multiply the log. Yes, trust me now to write 2 G's there. The log of, where's my white there? The log of A. Okay, so that's what I basically did here. I can now turn this into a negative and make this equal to 0. So I threw this over. And now I can remove a log of x. The log of x, and I'm left with x to the power 3 over 2 minus 3 over 2x is equal to 0. Okay, now here, if I solve this little log equation, let's just create some space here. I get, it's a product again. Remember we said if a product is 0, one of its components is 0. So the log of x is 0, or x to the power 3 over 2 minus 3 over 2x is equal to 0. Now this simply cannot be because this tells us that x is equal to 1. We know the log of that's 10 to the power of 0 is 1. And we have said that x cannot be 1. So that answer we are going to exclude here. Well, if you didn't use the log, some of you didn't use the logs most probably to approach this question. It is making this base here equal to 1 is also problematic. It's an exponential equation. So you cannot have bases that are 1 or negative. So unfortunately, we have to say goodbye to the x equals 1. Let's continue with the rest of this question. If you look carefully at what you've got here, folks, you can remove an x to the power of 1. Then you have x to the power of a half. Remember, this is 1 and a half. Minus 3 over 2 is equal to 0. So x is equal to 0, which is also not applicable. Or in this case, x to the half is equal to, what is it, 3 over 2. If I throw the 3 over 2 over, let me just see there. Yes, there we go. So therefore, my answer for x is the square of that, 9 divided by 4. The question is on the screen. It says, these 3 terms are the first 3 terms in a sequence. Prove that the sequence is arithmetic. So prove that we have an arithmetic sequence. Now, folks, there's 2 ways you can do this. What do we know about an arithmetic sequence? That's what we need to ask ourselves. What makes it arithmetic is the fact. So we can start off by saying to be arithmetic, I'm just going to leave it as that. Term 2 minus term 1 has to equal term 3 minus term 2. Now this can be written differently, and I want to use it in a different way. I want to show that twice, so I'm going to throw term 2 over, say term 2 plus term 2, there's 2 term 2's, will be equal to term 1 plus term 3. So I'm throwing that to the other side. And if I can prove that, then I know this is arithmetic. Okay, so and I think this is easier. It avoids using the fractions. So let's have a look. Twice term 1, or term 2 rather, is twice 2p minus 1 times by 2. Okay, so that gives you 2p minus 1. Now, if you go and you add term 2 and term 3 over there, term 1 and term 3. Yes, if we add term 1 and term 3, then we get 2p minus 1 over 3 plus 2 of those 2p's minus 1 over 3's. You might want to say that this here is the left-hand side of the equation. So in other words, we worked with that. Here we get this now becoming, if you look at 2p over 3, 2p minus 1 over 3, there's another 2p minus 1 over 3, but there's 2 of them. So that becomes 3 times 2p minus 1 over 3, and that is 2p minus 1, which is indeed the right-hand side. So we can conclude, because the left-hand side is equal to the right-hand side, the terms are in arithmetic, I don't want to write all of this out, are in arithmetic sequence.